Okay. All right. So normal distributions. First of all, why do we have to use a normal distribution for binomial problems? Because eventually, when the n gets too high, your calculator can't do that math anymore, because remember, it's like a part of the binomial formula is a combination, and the combination numbers get too large. So your calculator can't calculate that anymore, and you definitely can't calculate it either. Don't be like a book. Yeah, I saw you narrow your eyes. Noah, don't. So, do you see that if you have a binomial problem, that as you get more and more, your n gets higher and higher and higher, it looks more and more like a normal distribution? Because your average, whatever it is, will be most, the thing that happens the most, and then it will go away on the sides. This is an example where p equals 0.25. So, okay, so here's an example of this. Imagine that I've got a test, and it is multiple choice, and there is one correct answer out of 4 choices. That makes sense right now, where it says p is 0.25 and q is 0.75? So if you were to take a test that has 4 questions on it, it would be expected that you would get about 1 right out of 4 if you're randomly guessing. If it has 10 questions on it, it looks like the thing that's most likely to happen is 2 right. If you have 50 questions, it looks like you are most likely to get 12 right, but see how 11 right's pretty close, 14 right pretty close. See, like it starts making a bell curve. So the higher your n, closer it is to correct. There are 2 things you have to test to see if you can use a normal distribution to approximate a binomial distribution. They are, is it 5? Yes. NP has to be greater than or equal to 5, and NQ has to be greater than or equal to 5. So example 1 just says, can you use this normal distribution, or can you use a normal distribution to approximate a binomial distribution? All right, in a survey of adults in the United States, what % of people do you think have said that they have seen somebody walk in front of a moving vehicle without looking by using a mobile device?
67. 82.
It is a lot lower than that, but this was also, what was this? Did we find out 8 years old? So 34% as of 8 years ago. Okay, so they've walked and in front of a moving vehicle without looking. 82. Have you guys seen people walk in front of moving vehicles without looking with on their cell phones?
You ever seen the Pokemon Go videos?
No, but I don't know.
I can imagine. Kids running in front of cars. Do you have more of a story, or? No? Okay. He's like, you ever see those Pokemon Go videos? And I'm like, no. And he's like,
I have nothing else.
yeah. Okay, so you randomly select 100 adults in the United States, ask them whether they've seen somebody go in front of a moving vehicle without looking. So what do we have to test? See if it works.
N times the probability.
N times the probability of success. Probability of success is 0.34. What's the probability of failure? 0.66. Okay, and we have to see if 100 times P and 100 times Q is bigger than 5. Good job. Good job not picking up your calculator. Good job. I would really hope that you guys would know that 34% of 100 is 34, and 66% of 100 is 66. And these are both bigger than 5. In fact, if you know this in your head already, you, on your homework, don't even have to prove it. Just be like, yep. Just be like, yeah, N times P is bigger than or equal to 5. Do you have to test both?
No.
No, you have to test which one?
P.
Mm,
The lower.
the lower one.
Oh.
right?
In this instance.
In this instance, P, for sure. In this instance, P, but in general, the lower one. Test the lower one. If the lower one works, you know that the upper one works. If the lower one doesn't work, well, then definitely the upper one would work, but it doesn't matter. All right, now this is something called a correction for continuity. The problem with taking something that is discrete and putting it into a continuous function is that we are trying to take something that is individual things and putting it into a flowing bell curve. So we have to correct a little for that. So the correction for continuity is either adding or subtracting 0.5 to make the discrete distribution normal. All right, we're going to draw a lot of pictures here, where Nathan can show off his skills. What I want you guys to draw me like a bell curve that's made of like bars. Doesn't have to be exactly symmetrical on either side, but looking kind of like a bell curve. In fact, you're going to have to do that for all of these. How's your drawing looking, Justin? Look good?
Well, the first one does.
I do want to know.
And the second one.
Leaning Tower of Pisa.
Yeah. And the second one is it's like there's like a box in the middle too. It's like a box in like a
Georgia, you are capable of being nice about anything. Truly. And that wasn't the test. The test was yesterday, you not even getting to go on stage once and sitting there all nice and polite the whole time. And then me being like, sorry about that. And you being like, got some homework done. Like, you're just delightful and nice. I would have been mad about that, but okay. Okay. So let's assume, I know that I don't have enough bars in here, but let's assume that this is enough bars that has one bar for everything between 270 and 310, okay? I'm gonna call this bar number 270, and I don't know, this one over here, 310. Can you imagine that instead of 4 bars being between them, there's 30 bars between them? Because 270 to 310, no, 40 bars between them?